Okay, we are starting the lecture. Hi everybody. The lecture is going to be in English, right? My name is Stas Burov. I'm going to be the lecturer of the Statistical Mechanics 2 for this semester. Before we start, a couple of bureaucratic announcements. We have 3 hours per week lectures and 1 hour of practical studies. Each week you're going to have a home assignment. For the final grade, the home assignments, homeworks, is 11% of the final grade. During the semester, we're going to have 2 quizzes. Okay. And eventually, they are going to affect 22% of the final grades. Okay. There is a second chance quiz, moed bet, after the first 2 quizzes, if one needs it. Okay. The final grade, or the final exam, it's 67%. Okay. That's basically it. Okay, books, or the bibliography that I'm going to use. So I'm mainly using 3 books during this class. The first one is Calvin, and it's named Thermodynamics, or Thermal Physics, Thermodynamics. The second book by David Chandler. The name is Introduction to, or Modern Introduction, what's the name? Modern Introduction to Statistical Mechanics. So those are the 2 main books. Additional books are a book by Landau and Lifshitz. It is called Statistical Physics. And also book by Huang with the same name of Statistical Physics. Statistical Physics. All right. But as I said before, the main 2 references are book number 1 and book number 2. Okay, some personal information. I'm usually reachable by either email or in my office. My office is on this floor, room number 314. So building 202. Room 314. Okay. You can drop by anytime you like. There are no official office hours. As long as I'm available, I can actually sit with you. Okay, so basically, this is the whole bureaucracy that we have. Any questions so far? Great. There it is. Okay, so we will start. The first part of those lectures I think it will take us something like 2 weeks, is going to actually be not about statistical physics or statistical mechanics. We're going to repeat a little bit the stuff that you are all supposed to know, which is basic thermodynamics. But at least I will try to present it to you in quite a different manner than you, I think, than you learned it last year, basically by using some sort of a variational principles. So the first part, and this is what we're going to do for this week and part of the next week, is basically thermodynamics. Okay. Now, what is thermodynamics, and in general, what is statistical physics? Why do we learn it? Now, think about how you learn physics. From first year, you start by simply describing what are Newton's laws. So if I have a single particle, okay, classical particle, okay, and there is some sort of force that acting on this particle, let's call it F, I can always write Newton equation that describes to me how the position of the particle is going to change as a function of time. Okay? So we know that F equals ma. Let's assume that the mass of the particle is not changing with a function of time. So if I have an external force and I have a particle, everything is simple. Sometimes it's complicated, depends what the force is, but it's pretty simple. Now we can start to complicate a little bit the system, and we will say, well, what happens if I have two particles, m1 and m2? Okay. Now, what do we know? We know that if the forces, so we can have a general external force F that is acting on this system of two particles, okay? And we can also say that there is some sort of interaction between those particles. Okay? They are acting on each other, F12 and F21. Okay? Newton's third law says us that there is a relation between F12 and F21. They are equal by size and opposite by direction. Now, what we know that the system of two particles that have this kind of interaction between them can be always separated into an additional system, right? We can always treat a system of two particles as a motion of a center of mass, right? Okay. And some sort of a fluctuations, okay, we will define an additional coordinate, which is the distance between those two particles, and some additional fluctuations of this distance. Okay? So the center of mass is acting as it is a single particle that there is an external force acted on, right? And there are some sort of local fluctuations of the distance between those two particles that depends on the interaction force F12. Okay, easy enough, but still, even this simple system produces something pretty wonderful, right? We have Kepler laws, we can describe how the moon orbits the Earth, or how the Earth orbits the sun, etc., but still we're limited to the system of two particles. What happens if I add additional particle to this system? Okay? So this is one body. This is two body. What happens if I add even one single particle, additional particle, three body? Okay? I have M1, have M2, and I have M3. Very simple. Can I solve this? The answer is no. Why not? Well, because nobody has solved it so far. Okay, you can be the first. So for example, last month I read an article in Scientific American of a solution of a very specific case. People are working. This is an open problem. Some mathematicians are working on this problem when there are gravitational forces acting between those three particles, and what kind of stable orbits the system can produce. The general answer is that we do not know. We know something about the system, but we already do not know how, in general, the system is going to behave. Right? This is how limited our knowledge is. Right? When I'm talking about our knowledge, is our analytical capabilities of solving something. We can solve this, we can solve this, and then we're stuck. Okay? In the end of the 19th, beginning of the 20th century, French mathematician Henri Poincaré showed that actually starting from this system, you can get a chaotic behavior. What do I mean by chaotic? I mean by unpredictable. Okay? It's basically saying that if I'm starting from this configuration, or if I will move my M3 to some shift, I will shift it a little bit to the right, to the left, doesn't really matter where. Okay? And I follow the two systems as a function of time. After sufficient amount of time, the behavior of system A and the behavior of the system B will be completely different, okay, under specific circumstances. So we can actually obtain chaos out of three-body interaction system. Okay? Great. Now I'm teaching you physics. We are in a physics department. Physics is about the laws of nature. And what I'm basically telling you here, that we are stuck in three-body. Okay? We cannot solve this system. Now, I want to describe how this marker is actually wandering around. All right? There are 10 to the power 22 particles inside this marker. How can I actually imagine to say something about the motion of this marker when I know that I'm stuck with the three-body system? Right. Of course, is overselling to you this a little bit, because for the marker I can assume that it's actually not three-body. I can assume that all the particles here together are stuck, okay, in relation to each other. But still, okay, if I want to describe something that is a little bit more complicated than one particle, two particles, three particles, I have many particles. Real life systems are composed of enormous amount of electrons, atoms, molecules, whatever. Okay? How can I even imagine to describe something when I'm stuck? I know that I'm stuck, okay, with the three-body interactions. You studied analytical mechanics last year. So there is a very nice way of describing fantastic geometrical description of any physical system. And the claim of analytical mechanics is that I can always have a set of coordinates where the system is very simple. This is a general mathematical claim. The problem is how you can arrive to this very simple coordinates. There is no way to know how to describe a system with a lot of interactions. The way to do it, and this is what thermodynamics does and statistical physics does, is a way of averaging, right? What do I mean by averaging? I'm trying to say the following. You learned in physics 1 or mechanics, regular mechanics, that solid bodies somehow can be solved. There are additional constraints. There are conservation of momenta. There is conservation of angular momenta. But if I have a solid body, I can solve it. Although it's composed of a lot of molecules, I can still solve it. So instead of giving all those three particles whatever degrees of freedom, I'm saying if the particles are constrained in such a way that their positions are constant with respect to each other, okay, I can solve the system, because then I need only, again, one position. Okay? So this is one way of looking at the particles. The thermodynamics way of looking at the particles is as follows. If I'm looking on a chamber of gas, okay, and in this chamber of gas I have a lot of atoms. They interact with each other somehow. Okay? They're moving. They're pressing on each other and whatever. If I will try to write all the equation of motions of all the particles, all the interactions, I'm doomed. Why I'm doomed? Because even for three particles, I'm doomed. If I will freeze up the system, okay, such that all the particles won't move with respect to each other, I can again gain some sort of an understanding of this, right? Because then I will say, well, this chamber is behaving as one single big particle. Okay? So this limit I can also solve. Thermodynamics deals with the system then the chaotic motion of all the particles is such that I'm starting to forget about the single particles inside the system, and I'm saying I will have some sort of average behavior of all those particles inside. I do not discriminate all the particles. I do not say that this particle is very important. I'm trying to describe the behavior on average of this whole system. Right? So I'm losing information about what's going on the molecular level, what's going on with each single particle, but I'm saying that the whole system should behave on average somehow. Now, average is already a statistical word. Right? Why I'm using a statistic now? Because I'm losing certainty. I'm losing information. The moment I'm losing information, I'm saying I only have some sort of a statistical predictions. I have probabilities instead of certainties. And this is the language of thermodynamics. I forget about local information. I gain an average information of what's going on average with the system. Okay? And I'm using experimental observations in order to deduce some physical laws, like the laws, first thermodynamic law, the second thermodynamic law, the third thermodynamic law, in order to describe the system as a whole. Right? So this is what we are going to try and produce now in the next hour, to describe the system from a general perspective without going inside and saying, well, I have a particle over here and interacts with this particle that somehow interacts with that particle. There is no way out of it. We can. Even the quantum computer, we cannot simulate system with 10 to the 22 particles inside it. Okay? So we are bound into saying something about statistical properties of the system. Now, is it good or is it bad? Well, you can say it's bad, Stas, because you do not know all the knowledge. But actually, or you fail to produce all the possible knowledge of the system. But sometimes I do not need to know everything. I need to know something, some properties. And how it comes out is that some of the properties can actually be deduced with very simple laws, the laws of thermodynamics. Any questions so far? No? All right. Now it's quite fascinating, okay, so that eventually the statistical approach works in a very general situations. So I can describe a system, okay, of a spreading particles in a gas. The same physics will describe the motion of a particle inside a living cell. The same physics will describe intracellular radiation, okay? And the same physics will eventually describe some artificial intelligence algorithm searching for an optimal solution. Why? Because if at some point I forget what any of those particles are doing, and I'm only leaving some very important and critical information, okay, due to the fact that I have many particles, okay, the laws are exactly the same no matter what those particles actually are. Okay? So because of the fact that we are using huge number of particles, the proper identities of those particles are not important. There are some only very few specific facts that matter and nothing else. And again, this is only due to the fact that I'm working in a system that has already 10 to the 22 or something number of particles. So my approach, the statistical physics approach, will work with macroscopic systems. It won't work for 3-body, okay, because here is everything important. It won't work for 10 particles, but for 200, 300, 10,000, it will start to work again. All right, so we are starting by stating some basic laws of thermodynamics. Now, thermodynamics was developed in the 19th century. People measured properties of gases. They cooled gases, they heated gases, they compressed gases, they expanded gases. And surprisingly enough, they gained huge amount of information about not only of how gases are performing under all these changing conditions, but they also deduced some general laws, which are the laws of thermodynamics. You must remember that this is the 19th century. The math is the mathematics of analytical functions. So this assumption of all those guys from the 19th century is that when I'm looking on a gas, I'm not looking on a single particles that are composing it. I do not have an atomistic model. There are no atoms. There is some homogeneous substance. And when I'm trying to describe this gas, this substance, I must use properties of homogeneous functions. Okay? So one can basically state that all the thermodynamics that you have learned so far is properties of analytical functions plus 3 or 4 physical observations. That's it. Okay? So we will start with 2 observations that constitute the 2 laws of thermodynamics. So the first law of thermodynamics is what? Simply conservation of energy. Now, like very fancy title, the first law of thermodynamics, but it's conservation of energy per se. What it basically means. Let's assume that I have a system. Okay. There is a separation. I'm trying to say that there is something that I call an internal energy of the system. Okay? If this is my system, the internal energy of the system is E1. This is my system, the internal energy is 2,2. And from what I know, at least from 19th century perspective, the energy of the system is an extensive property. The bigger my system is, the bigger my energy is. Right? So basically, the energy, I write it down, energy is an extensive property. What this means, it's proportional to the size of the system. Okay, so how I understand this now, let's assume that I have a gas, and the gas is composed of a lot of atoms. I increase the size of the system by 2. I have much more molecules of gas now. Each molecule contributes me a quantity of an energy, right? So the system grew by the size of 2. The energy also grew by the factor of 2. That's it. That's all the story about energy is extensive property. Now, what I know about energy, I assume that the energy is always conserved. How I can change an energy of the system? I can perform work on the system, or the system can perform work. Right? So the change in the amount of energy of the system is that I can perform some sort of work. Is this the only thing that I can make the system change the energy? Heat, right? I can heat. I can transfer heat into the system, and after I transfer heat inside the system, I can make the system do some specific work, right? Very simple example, right? I have a bulk of water. I heat it up. So I have a fire over here. The water starts to boil. Okay. The water starts to boil. There is some vapor going up. I have some sort of a propeller over here. Okay. And due to my heating up of the water, the propeller starts to rotate. I performed or I used my system and transferred heat into some positive work by rotating this propeller over here. Okay? So when I'm saying that I've changed the energy of the system or transferred some of the energy of the system from one part to another, I'm saying I also added some sort of a heat to the system. Now this is not a full differential. I have this mark over here because I can also only, I can only measure differences of the heat that I transferred inside the system. Okay? Now we understand heat. This is something that related to atoms, 19th century physics. Heat, I heat the system. Questions? No? All right. So the first law of thermodynamics is this equation over here, which is simply conservation of energy when I'm thinking that the energy can be modified only by performing work on the system or by the system, and the flux of heat inside of the system or outside of the system. All right. Now let's see what is work. So this is energy. This is work. This is heat. What is work? Well, it depends on the system that I have, right? In general, I can say the following. The amount of work that the system have performed, okay, a mechanical work, let's call it like this, is some sort of a generalized force, F, I don't know, the force will depend on the system, multiplied by a mechanical extensive variable, dx. What is dx? It's some variable that it's related to the size of the system. Okay? X define the size of the system. What x can be? So for example, x can be volume, right? So for example, if I'm changing the size of the system by some dV, and the external pressure is P, okay? The amount of work that was performed is minus P external dV. Okay? Another example, for example, if I have tension, so I have a rubber band, right? So I pull the rubber or squeeze the rubber, okay? The amount of work that is performed depends on by how much I extended the rubber multiplied by the tension of the rubber. Okay? This is also dW. But in general, I'm saying I have some sort of a force. I have some external macroscopic mechanical variables that dictate the size or define, the size of the system. And when I want to talk about macroscopical work that was performed, okay, it's simply the force multiplied by the change of this variable. Okay? This is also how work is defined. How work is defined in regular mechanics. Now in general, when I'm looking on F, I'm saying this is a vector. So when I'm talking here, what is F dot dx? This is a simple multiplication, scalar multiplication of a vector by a vector. So it's simply F1 dx1 plus F2 dx2 plus F3 dx3. And it will all depends what my variable x is. So basically, controlling forces and mechanical works is easy, right? Always return to this example of a gas. I can squeeze the gas, I can extend the gas. It's very simple. Okay? What about the heat? So the heat is a little bit more complicated, right? because I need to control the heat. So I can heat up the system, burn some other substance, okay? And this is how I can transform some sort of heat inside the system. Now, sometimes I want to conserve the amount of heat inside the system, to control it. How I control external work, okay? For example, I can make sure that the volume of the system is not changing. I can make the volume of the system constant, or the size of the system constant. This is how I control that a specific amount of work is performed or not performed. With the heat is a little bit trickier, right? Now, I am assuming that there is something which I called adiabatic walls. What are those adiabatic walls? For me, it's a constraint that I can impose on the system, and adiabatic walls prevent the flow of the heat inside or outside of the system. Okay? So basically, the moment I impose adiabatic walls on the system, I'm saying the amount of heat is staying constant all the time. Nothing changes. How I basically can create adiabatic walls? So use your imagination. Okay? Usually, the best adiabatic walls are composed of some layer of a vacuum, okay? Because heat eventually is transferred by motion of molecules or atoms. And the moment that I have a vacuum layer that prevents the motion of the atoms, basically there's also no flow of heat. But again, this is an atomistic view. The view of thermodynamics is, well, we don't know what atoms are. Okay. So I defined energy, I defined a change of energy. I defined microscopic variables, A. I defined heat, well, loosely saying that I can heat up the system. I defined something that I can impose on the system that can prevent of the heat to flow outside. Okay? And now I will start to say, well, by changing all those different constraints, by changing the external parameters, by changing, imposing, or taking off adiabatic walls, I can change the state of the system, right? For example, if I have a chamber with a gas, so here is a gas. I can put additional weight on top of a piston that's over here, okay? And by adding more weight, I can change the size or can change the pressure. And this is how I can change what I called a state of the system. Okay? So the values of all the different x's and the presence of adiabatic walls dictate, this is what can I observe from my experiment, they dictate a state of the system. Okay? And now I'm saying by actually constraining my external variables, excess, existence or non-existence of adiabatic walls, I can constrain the system to be, or make the system to be in a specific state. I change one of those variables, and the system transfers from one state to another. And the question of thermodynamics is, how can I describe those different states? What are the properties? What are the properties of different states of the system? Moreover, what I notice is that there are equilibrium states. What I mean by equilibrium states? Let's consider that I constrain the volume of the system. I constrain the amount of heat that I have actually fluxed inside the system. I imposed adiabatic constraints and adiabatic walls. I left the system to rest for a while. And then I see that it reaches a state, what I call a state, that is not changing as a function of time. I'm not concerned by how long it have taken me to reach the state. I'm only saying that after a while, the system will reach a specific situation that I call an equilibrium state. Okay? And what I notice that in order to define this equilibrium state, I do not need to know all the knowledge about all the different constituents. I don't need to know what molecule A and molecule B does right now. Okay? This is my averaging procedure. I'm thinking that the equilibrium, this marker is an equilibrium, it does not move as long as I won't move my arm. Okay? There are some sort of different interactions that's going on inside, but nothing drastic happens. The marker stays the same. For me, it's an equilibrium system, and it's only defined by some external constraints, external variables. It's defined by the amount of heat that it's inside, and it's defined by all this excess that I constrained. Okay? And the question of thermodynamics is how a system can go from one equilibrium state to another equilibrium state. What can I do, or how can I understand those transitions? Okay? I have equilibrium state A, I have equilibrium state B. How I can make the system go from one state to another? Okay? What is going to change inside the system if I'm changing some external variable? What is the new equilibrium state that I will reach? Okay? So thermodynamics is concerned only with equilibrium states. We are assuming that the system is homogeneous, right? We are assuming that the energy of the system is extensive, it's proportional to the size of the system, and we are assuming that we always can reach, on a normal time scales, equilibrium state. All those assumptions are not always true. There are systems that will never reach equilibrium. For example, glasses. Okay? Glasses that you have on here in the window, right, is a system that is out of equilibrium. Okay? It looks to you as it's actually not changing nothing with this glass, but if you will measure the thickness of a glass as a function of time, we will see that the thickness is actually changing. Slowly, slowly, little by little, but it's still changing. The glass is actually in a flowing state. Very slow growing, very slow changing state, but it's still not in equilibrium. Okay? It's a surprising situation. So there are some exotic systems that will never reach equilibrium. We will, or at least thermodynamics is concerned only with systems, like gaseous systems, that someday will reach equilibrium. Okay. Yes?
The example with the glass, is because of property of the material?
Yes. So eventually there are some interactions inside the glass. It's what is called, it's actually a mystery, right? So there is a question